Okay, here we go, guys. 15.4 is all about integrating in polar coordinates. Before we talk about integrating in polar coordinates, I want to give you a common sense way to think about a double integral. So, a generic double integral looks like this. We integrate over some region in the xy plane. Typically, we call that region R or D. And the integrand is some function with two inputs, f of x, y, dA, where dA consists of two differentials with either the order dx dy or dy dx. And if you remember how we define the integral, it's really the limit of a Riemann sum created by breaking up the region R into a grid. So if this is the xy plane and your region R is inside this blob right here, then what we did, I'm not going to recreate the Riemann sums, but what we did was we broke up R into a grid of rectangles, smaller rectangles, right? We did this, R was a rectangle when we did this, but you can do something similar when R is not a rectangle. And if you focus on one of these little sub-rectangles, say this one right here, okay, let's take it out. The dimensions are really delta x and delta y, but we can think of them as dx and dy. So that dA is an area element. It's the area of one of these infinitesimal little boxes. And then if you recall, we set up the double Riemann sums according to this grid of rectangles, and we took the limit of the Riemann sums as the number of, well, you could think of it in a number of different ways, but as this mesh gets finer and finer, we take the limit as this mesh gets finer and finer, which means the number of sub-rectangles goes to infinity. And if that limit exists of those Riemann sums, we get the integral. So we think of dA as being an area element. Now, I'll come back to that idea in a minute, but let's talk about polar coordinates. So polar coordinates, first of all, it's an alternative way to represent a point in the xy plane, right? Instead of using an x and y, you use an r, which is a distance from the origin, and a theta, which is an angle between the positive x-axis and the line segment made between the point and the origin. So if you wanted to draw a picture of it, it's really easy. Let's say you have the xy plane and you have a point. Then theta, the angle, I'm drawing this line dotted because it's not really part of anything. Theta might be that angle. Of course, there's multiple representations for theta. And r would be the length of this line segment. So you could represent this point by xy, but you could also represent it by a point r comma theta. You guys are very familiar with that from Calc 2, right? And then you're also familiar with some conversion equations. So if, you know, when you drop the perpendicular, you get a nice right triangle. And you know that this side is x, this side is y, and you can come up with some conversion equations. So you can use these equations to convert one way or another from either polar to rectangular or rectangular to polar. So just remember those. Hopefully you already know those, but you know, in math you have to be in a constant state of review. So it doesn't hurt to name those again. Okay, so remember this grid of rectangles up here? Well, what if we split up R not into a grid of regular rectangles, but into a grid of polar rectangles? What would that look like? So now, let me kind of not reproduce that picture above exactly, but let me produce an R, a region R that would be conducive to setting up using polar coordinates. One that would be conducive to setting up polar coordinates might look something like this. You might have a function like this. Maybe, it would certainly be helpful if you could call it a function of theta. So R would be g of theta. Let's call it G2. R2 is G2 of theta, because I'm going to have an R1. And maybe there's an R1 over here. So if you can represent R1 as a function of theta, a boundary curve to the region capital R as a function of theta, then that's a big hint that, well, maybe polar coordinates would be a good idea to use here. And then maybe you can talk about the region from an angle, maybe theta 1, and this would be a constant, theta 1, to an angle, say, theta 2. If R is your region between these guys, then, so I'm going to erase this in a second, but can you see what I'm talking about? R would then be this region, outlined in green, I suppose. That's R. So if the boundaries, some of the boundaries on R are defined by just constant values of theta, and two of the boundaries are defined by, for instance, it doesn't have to be two. I mean, you could define a boundary as being a circle centered at the origin, and then it's just R equals whatever the radius of the circle is. So this is just for instance. If you can define two or one of the boundaries as a function of theta, then you're in business. Maybe you can convert to polar coordinates, and maybe things will get a lot simpler, I guess is the idea. So then how do we break up this region R into polar rectangles? We do it using radial lines from the origin. So we could keep going like that, but I'll just draw it like so. So radial lines from the origin going one way, and then arcs going another way. And if you look at these things in the middle, they're not quite rectangles because these lines that I'm drawing now aren't lines, they're arcs, really arcs of a circle. But if you were to zoom in really close, let's go up to 200. I mean, does this guy right here look all that much different than a rectangle? It really doesn't. And as the grid gets finer and finer, those polar rectangles look more and more like, well, regular rectangles. So the idea is we're going to adjust the double integral and write it in terms of polar coordinates. So let me pull out. Let me focus on this polar rectangle and pull it out. So a polar rectangle then, these lines would definitely be straight on the side, but these sides would be arcs of a circle. So that if you extended the side faces here and here, they would meet up, these lines would meet up at the origin 0, 0. Right there, right there. Okay, so this then is our region, our sub-region, our subpolar rectangle. And I would like to find an approximation for the area of that. Well, this angle here, we wouldn't call it theta, we could call it the change in theta. A change in theta. And since this guy is an arc length, if we call this distance, say, from the origin to, say, this bottom arc, if we called that distance r, I think we could use a familiar formula to get the length of this arc right here. In fact, does anybody remember the arc length formula for so if you just think of a circle and the crust of the length of the crust of the pie, which would be in black right here, and if this is theta here, and we call that length of the crust of the pie s, and we call the radius r, does anybody remember what s equals? R times theta, right? That's the length of the crust of the pie right here, isn't it? Well, we could then say that the length of that crust of that particular piece of pie would be, well, not r times theta, but r times delta theta. Thinking of that as a change in theta. And then we could think of this side right here as a change in r. This side right here could be a delta r, because delta r over this this little subpolar rectangle, r is changing from whatever this length is to here. So this smaller length right here is delta r. And so we could say that the area of this polar rectangle, this is not exact by any stretch of the imagination, but the area of this polar rectangle is approximately, well, how do we find the area of a regular rectangle? We multiply length times width, right? So that's exactly what we're going to do here. We're going to take delta r times r delta theta, or the way most people would like to write it is r delta theta, just rearranging the multiplication. Now, we could, in an analogous way to how we set up Riemann sums in rectangular coordinates, we could set up Riemann sums for this grid of quote-unquote rectangles, right? And then we could take the limit of that Riemann sum. It would actually be a double Riemann sum. And if that limit exists, we're going to call that a double integral. But what is it going to look like? What would that double integral look like in comparison with the double integral over r of, say, f of xy dA? What would that look like? Well, the region is still r. And I'm referring to this r, although I wouldn't want to set it up in rectangular. I'm referring to this region here in between the green lines, or curves rather. The region is still r. That hasn't changed. But if you're going to convert to polar coordinates, you got to change x, right? X is r cosine theta. Y is r sine theta. And the area element, dA, is going to become, well, I kind of want to squeeze it in right here. It's going to be r dr d theta. So dA, the area element, becomes r dr d theta when you take the limit and make that grid that splits up r finer and finer. Assuming the limit exists, we use the notation r dr d theta on the end of it as our area element. When the function you're integrating is equal to 1, then what are you actually finding? When f is, so note, when f, the function you're inserting into the integrand, is 1, then the double integral gives you the double integral over r, I'll be generic here, of just f dA gives you what? Remember, it gives the area of r. That's something every Calculus 3 student needs to know. It gives the area of r. And in this question, we're asked to find the area of one petal of the rose curve given by r equals 3 cosine 2 theta. Well, I mean, that's a polar function, right? That's a big clue that you're going to integrate in polar coordinates. Okay. So somehow we have to find our limits of integration, and that's what this problem is going to involve mostly. So right now I have to remind you of what this rose curve looks like. I really don't need all of it. It's so symmetrical I can graph half of it and get the answer. So if I want to graph part of that rose curve, I mean, you may remember there are going to be 4 petals to this rose curve. If n is even, you double n, and that n is 2. If n is 2, you double it, and you'll get 4 curves. We only need part of that curve, and I can get it just by plotting a few points. So let me show you how that's going to work. Here's my plane, and then I'm going to plot a few points r theta to get an idea of what 1/2 of a petal of this rose curve looks like. I'm going to start with theta equals 0. Let's see, what's going to produce... what's going to bring you back to theta equal to a radius of 0? What's going to bring you to a radius of 0? Well, if we end up taking the cosine of pi over 2, won't we get 0? So I think if we plug in pi fourths for theta, we'll have 2 times pi fourths. That'll be pi over 2, won't it? Cosine of pi over 2 is 0. Okay, so I want to include that one in there, and then maybe one in between. I'm thinking pi sixths. You'll see why in just a second. Okay, let's calculate now. You plug in for theta, and then you calculate r. So if I plug in 0 for theta, I've got r equals 3 cosine of 2 theta. Whoops. R equals 3 cosine of 2 theta. If I plug in 0 for theta, I end up taking the cosine of 2 times 0 is just 0. So the cosine of 0 is 1 times 3 is 3. So r equals 3, theta equals 0. Whatever point that describes is on the graph. I'll show you how to graph that in a second. If I plug in pi over 6, what do I end up taking the cosine of if I plug in pi over 6 here? 2 times pi over 6 is pi over 3. Oh, and the cosine of pi over 3 is what? A half. That's why I plugged in pi over 6. I knew I'd get a nice number. So I get 3 times a half, which is 3 halves. That's 1 1/2. That's not hard to plot. R equals 1 1/2. That's not hard. So 3 halves. And then as already discussed, when I plug in pi over 4 here, I end up taking the cosine of pi halves. And we know that the cosine of pi over 2, or 90 degrees, is 0, right? So 3 times 0 is 0. So let me remind you real quick how to plot points in polar coordinates. So even though I drew an x and a y axis, I'm going to think radially. So I'm going to go out, well, it looks like the furthest I have to go out is 3. So from the origin, which is called the pole in polar coordinates, I go out a distance of 3. And then what's really nice to do is to graph using polar graph paper, which is just concentric circles. So here's a quarter circle of distance 1 from the origin. Here's another quarter circle of distance 2 from the origin. Here's another quarter circle. Well, it's flattened out a little too much. Let me fix that. Another quarter circle of radius 3 from the origin. And I could go all the way around, but I'm not going to need to, as you'll see. So if I want to plot the point 3, 0, well, it does happen that 3, 0 in polar coordinates corresponds with 3, 0 in rectangular coordinates. But you think differently. You think, okay, what I like to do is I like to look in the direction of 0, which corresponds with the positive x-axis. So I look in that direction. Look from the origin to the right. And then I go out a distance of 3, and it's that point, isn't it? Now look in the direction from the origin. Look in the direction of pi 6. And I'm going to erase this in a second, but pi 6 is really what in degrees? About 30 degrees. So I'm looking in this direction approximately, right? I'm going to erase that because it's getting in the way, but that's the direction I'm looking in. And I go out how far? 1 1/2. So from 30 degrees, 1 1/2, I'm thinking right about there. It's just an estimate, right? Good enough. Oh, and then at pi over 4 splits the quadrant in half, 45 degrees, but I don't go out anywhere. I go out 0, so oops, I just stay where I'm at. I stay at the origin, right? So right here is where I'm at. And if you remember how these rose curves go, well then if you draw this thing as theta gets bigger, you just connect the dots like so, and you really get half of one of the petals of the rose curve. And that's all you're going to need, because the petals are symmetric. Okay? And you're just asked to find the area of one petal. So if you find the area of 1/2 of a petal, what do? Just multiply by 2. Okay? So let me then zoom in on this and show you what we're going to do here. Let's go 200. We can't go any further. Yes, we did it. Okay. So remember how I set up either a vertical rectangle or a horizontal rectangle when setting up the limits of integration in rectangular coordinates? You don't do that here. You use a sector. You use a representative sector as opposed to a representative rectangle. Or just a line segment, a radial line segment, a spoke from the origin would do. So draw a spoke from the origin. That would look like this. Somewhere so that the initial point's at the origin and the terminal point goes to the function, which is given by the curve. Okay? Now keep this picture in mind. I gotta back off the view a little bit. Let me go to 150. Okay. Keep this picture in mind as we're setting up the integral. So The generic setup, well, you guys all know you need a couple of integral symbols, right? You automatically have r dr d theta. And when you're finding area, the function is just 1. So for emphasis, I'll plug in 1 there. But you don't need it. So what I'm saying is, f is 1. We're just finding the area of the region then. Okay? Now, the limits of integration, the inner limits of integration give you r in terms of theta. And they can often be constant, but they're not both constant here. So r, look at this representative sector in green. It's really just a spoke of a line segment radiating out from the origin. What's the bottom of, or the initial point? What's the initial value of r on this line segment in green? 0. That's your lower limit. What's the final value of r as you go all the way across? It's the function value, isn't it? Which is, and remember we have to multiply by 2, and I'll do that in a second. It's 3 cosine 2 theta. So the upper limit of integration is 3 cosine 2 theta. I'm going to multiply the whole thing by 2 because if I don't, I'll only have area of half of it. So this is the area of one petal, except I don't have the outer limits of integration. So the outer limits of integration are what theta range from, and we're never changing the order of the differentials here. So theta is always going to range between a constant and a constant, and you can get it by looking at the theta values in this table. What theta value produced this point that we started with? 0. What theta value produced this point that we ended at? Pi over 4. So we're going from 0 to pi fourths. And that's your setup. Any questions on the setup? Is that okay? All right. Now, this is worthwhile evaluating because we're going to get some good review here. It's not that it's a hard integral to evaluate, but you do need some techniques from Calc 2 in order to get it done. So one thing I want to point out is, well, I'll save that point for later, actually. So let's just get to it. Notice what the integral says. It says to integrate with respect to r first. So I'm going to leave this 2 out here. I'm going to leave the integral from 0 to pi fourths. And I'm going to do the inner integral first. Okay, what do I get when I integrate r? R squared over 2. But look, and pay attention, this is important. The way you organize your information can help you avoid mistakes. It's r squared over 2, but do I need that to keep that division by 2 inside? No, it's a constant. I can put the division by 2 outside, right, and not clutter things up. And then what am I evaluating r squared from? From 0 to 3 cosine 2 theta, right? 0 to 3 cosine 2 theta, and we still have the d theta, right? So we're just evaluating the inner integral right now. Is that clear? And look how it's just going to be much nicer to evaluate now because now the 2's cancel on the outside. And what do we get when we apply the fundamental theorem? We just get 3 cosine of 2 theta squared, right? Which is 9 cosine squared 2 theta minus, well, 0 squared. Is that going to do much? No. So I'm going to write it like this. Oh, now what could I have done with that 9? Write it on the outside. Make life easy. Write it on the outside. I'll do that in the next step. Now, do you remember how to evaluate a cosine squared? What do you have to do? This is from Calc 2. Rewrite it how? You're on the right track. It's a power reducing identity that you have to use, right? Now the power I'll write it off over here to the side. Usually we write it in terms of just the cosine of squared of theta, right? And so the power reducing identity is actually 1 plus cosine of 2. You double the angle. 2 theta all over 2. But since it's 2 theta to begin with, you double it. What happens? It makes it 4. Yeah. Also, this division by 2, can I pull that out in front of the integral? Yeah, make life easy. So that means that'll come out as a 1/2, but I can also bring the 9 out, so that comes out as a 9/2. Integral 0 to pi fourths. And then we just end up with 1 plus cosine of 4 theta in the integrand. Now, does that make sense to you guys so far? So let me try. I can't quite get the whole thing in the picture, but almost all of it. Does that all that make sense so far? Okay. So let's integrate. 9/2 on the outside. We integrate 1 with respect to theta. What do we get? Theta. We integrate cosine 4 theta with respect to theta. We get, well, it's going to involve sine of 4 theta, but you have to do something here. You have to multiply or divide by something. You multiply by 1/4. And in fact, anytime you have a constant here, like the cosine or sine or maybe e to some constant times x, anytime you have a constant here, then when you integrate, you multiply outside by 1 over that constant. Then you can check it, right? Just take the derivative of sine of 4 theta, 1/4 sine of 4 theta, and you'll get cosine of 4 theta. Because by chain rule, you'll have to multiply by 4, and the 4 times 1/4 will reproduce that 1 right there. So you can use U substitution on that, right? But this is one particular instance where it's just easier to memorize that trick for integrating because it comes up so often. Is that okay? All right. So I meant to write a theta right here, didn't I? And I started talking about something else. Okay. Now we plug in pi fourths, and what do we get? Let's see, pi fourths right here. But when we plug in pi fourths for theta, what do we end up taking the sine of? Pi. What's the sine of pi? 0. So just pi, I can write it out. Pi fourths plus 0 minus, what happens when we plug in 0? I think both, we get 0 for theta and sine of 4 times 0. Sine of 4 times 0 is sine of 0 is 0, right? So for completeness, I put it in, but I guess we didn't really need it. So what do we end up with? 9 pi over 8. And what kind of units would that be in if I had given you units? It would be in square units because we found the area of R, right? So here is another problem where you're just given an integral and you're told, hey, evaluate it. But let's look at this thing. First of all, start with the integrand. I see the square root of x squared plus y squared, dx dy. Okay, that's kind of ugly. In case you weren't sure, that's kind of ugly, right? When you see an x squared plus y squared, either in your limits of integration or in your integrand, a little alarm bell should go off in your brain and say, hey, use polar coordinates because x squared plus y squared is just r squared in polar coordinates, right? Yeah. Now, you're going to have to translate to polar coordinates, which means you got to figure out limits of integration here, which usually means you have to draw a picture unless it's super easy. So how do we do that? Well, I know that since it's an order of dx dy on the differentials, I know that x is between the lower and upper inner limits of integration. So I know x is between y and square root of 8 minus y squared. Likewise, for the outer limits of integration, what do I know? I know y is between 0 and 2. And this defines R. This defines R. So let's draw it, okay? It's hard to picture it even with these inequalities. Let's draw it. So, okay, I can do that. Whoa, that was not a very straight x-axis. Okay. Okay, first off, I can draw, okay, you want to draw the equalities, right? So y equals x, That's pretty easy, right? So y equals x is the 45-degree line, isn't it? Something like that anyway, y equals x. Now this other one, x equals the square root of 8 minus y squared. It's more recognizable if you square both sides. Get x squared equals 8 minus y squared. Add y squared to both sides. X squared plus y squared equals 8. Oh, okay, what is that? It's a circle of radius root 8. That's part of the circle right there. X squared plus y squared equals 8. Okay. So what do I know? Well, I have the differential order dx dy, which means horizontal rectangles, right? Representative rectangles. That's important to realize. Horizontal representative rectangles. So I'm not sure what my area is yet. Is my R in here? Or is it in here? Well, if you draw your a rectangle appropriately, you'll be able to tell. It's got to be in here. Whoops, I meant to change colors there. It's got to be here. This has to be your horizontal representative rectangle. Why? Because if you look at the left end of the rectangle, that's y. If you look at the right end of the rectangle, that's the circle, right? And then if you think about what this point has to be, this point has to be what? I think it's got to be 2, 2, doesn't it? How could you tell for sure? Well, you could just set, I mean, it occurs on the line y equals x. You could just set x equal to y, right? And then in the circle equation, then you get x squared plus x squared, which is 2x squared equals 8, or x equals 4, which means x equals, in this quadrant, x equals 2. Right? And if x equals 2, y has to equal 2 because it's on the line y equals x. So yeah, this has to be right. So furthermore then, for the second grouping of inequalities, I know y has to go from 0 to 2. Certainly, you could think of any horizontal rectangle being drawn from a height of 0 up to this height of 2. Okay? So that's got to be the right picture. In other words, this has to be R. So R kind of looks like a little piece of pie, I guess. Now, to set up the equivalent integral in polar coordinates, we're going to draw a representative sector, but I usually just draw a spoke. So my spoke is going to look, whoops, it's going to start at 0, 0 here, and it's going to go to the boundary given by the circle. Can you guys see that okay? All right, now let's set up our little template. So our integral is going to be, it's going to look like that. It's going to have the area element r dr d theta. Don't ever forget that extra r in there. And then what does the integrand become? The square root of r squared, right? X squared plus square root of x squared plus y squared. X squared plus y squared is r squared. And that's multiplication right there. Now, the limits of integration on R. What does R range between? R goes from 0 right here to the end right here. So from 0 to what? In polar coordinates, it's just the radius of the circle, isn't it? So what's the radius of this circle? Root 8. So it goes from 0 to root 8. And then even better, or even easier maybe, your outer limits of integration. Okay, think of where does theta start at? So you think angularly. If you were going to carve out this region, remember theta goes positive theta goes counterclockwise, so that the x-axis corresponds to a theta of 0, and the line y equals x is the 45-degree line, so it corresponds to theta equals pi fourths, right? That's the whole ballgame. Theta, or at least for the setup, theta goes from 0 to pi fourths. Look how much better this integral is. In fact, it gets even better because if you take the square root of r squared, you get r. R times r is r squared. And you get the integral 0 to pi fourths of the integral 0 to square root of 8 of what? Just r squared, right? dr d theta. So that's what our given integral is equal to. Okay? So the given integral equals this lovely character. Now, that looks a lot easier to integrate, and in fact it is. And I want to remind you of something. The limits of integration are constant, right? And you can think of the integrand as a function of just r. When that happens, you can split this into a product of integrals. So this will be equal to, so to make it even easier on you, this will be equal to the integral, so from 0 to pi over 4, there is no function of theta, so it's just d theta. I mean, you could think of it as 1, d theta, times the integral from 0 to root 8 of r squared dr. That's how you can split up the integral. If you can split up the integrand as a function of r times a function of theta, since there's only a function of r, you're good to go there. And the limits of integration are constant, this will always be true. And it makes it even easier to integrate. What's the integral of 1 d theta from 0 to pi fourths? It's just pi fourths. It's just the upper limit. If you don't believe that, go ahead and integrate it. You'll get theta evaluated from 0 to pi fourths, which is just pi fourths. Well, this guy's a little bit harder. What do I get when I integrate r squared? 1/3 r cubed. But remember, I leave the 1/3 on the outside. I'm just going to evaluate r cubed from 0 to root 8, which is just root 8. So I get what? Pi 12ths? No, I said a second ago just root 8. I meant you're going to insert root 8 and it'll be root 8 squared or cubed, right? Root 8 cubed. Does everybody agree with that so far? And then, I don't know, if you like simplifying radicals, you could have a good time here. Pi 12ths. Well, what's the square root of 8? It's 2 radical 2, right? So what do you get if you cube that? Well, certainly if you have to apply the exponent to the 2, so that gives you 8. And radical 2 times radical 2 is 2 times another radical 2. So what do we end up with when all is said and done? Well, I don't know. We end up with, well, this is 2/6, right? And then 8/6 is really 4/3. So how about 4 radical 2 pi, if we write it that way, over, what did I say, 3? That would be a way to do it. Let's find the volume of the solid bounded above by z equals the square root of 16 minus x squared minus y squared. Outside of the cylinder, x squared plus y squared equals 1, and above z equals 0. Let's start with z equals that square root of 16 minus x squared minus y squared. It might be more recognizable if you do what to both sides? Square both sides. That gives you z squared equals 16 minus x squared minus y squared. And then what else could you do to make it even more recognizable? What is this? What does that mean? There you go. Bring the x squared and y squared to the other side by adding. And you get x squared plus y squared plus z squared equals 16. What is that object? It is an ellipsoid, but even more specific, it's a sphere. And so we could actually leave it in the standard form of a sphere. Realize what's the radius? Sphere. The center, C for center, capital C for center. What's the center of this thing? The origin and the radius. I don't want to use r here because I don't want you confusing it with the r from polar. So I'll write out the radius is 4. Okay. However, it's just the top half, right? Because originally we were given z equals the positive square root. So that means it's the top half because it's the positive square root here, right? Top half of sphere. So let's see if we can draw a picture of that. So we're drawing a hemisphere, right? The top half. Something like that. And we got to give it an equator, which I suppose isn't really an equator. I guess it's a base. But if it were a full sphere, that'd be the equator, right? My equator looks a little wavy, but that's okay. It'll do. Okay, so that's part. That's part of the solid. Now, it's got to be outside the cylinder. You guys remember what the cylinder x squared plus y squared equals 1 looks like? It's a circular cylinder, right? Circular cylinder, right? Of radius 1. And if you graph it in just the xy plane, it's the unit circle, isn't it? So in the xy plane, if that's the origin right there, then the unit circle might look like that. And then if you extend this up, eventually it's going to bust through that hemisphere, isn't it? It's going to bust through, I don't know where. Maybe right here. And then, okay, it'll bust through, and then it just keeps going up forever and ever and ever, doesn't it? Okay, and then the xy plane is right there on at the base, xy plane. That's z equals 0, right? Okay. So what region then are we looking for? What volume are we trying to find? Well, it's the volume outside of the cylinder, but still underneath that hemisphere. So again, it takes some time to interpret this. Find the volume of the solid bounded above or on the sides, same thing. Technically it's above, by the hemisphere, outside of the cylinder, but above the xy plane, right? Z equals 0 is the xy plane. So what does that describe? It describes the volume surrounding the cylinder, doesn't it? Which is kind of hard to draw. I don't know how to draw it. Just kind of in here, but not, outside that cylinder, right? Okay. All you really need here is the region in the xy plane. Realize the roof is given by the hemisphere. The roof of your structure is given by the hemisphere. And the floor of your structure is given by the xy plane, except it's got to be outside that cylinder, which is the circle in the xy plane of radius 1, center 0, 0. So what's it going to look like? Well, if you think about this picture a little more, it's going to be a donut-type structure. You guys see it? This region in the xy plane is going to be this donut right here. And so if we draw the circle of radius 4, which represents the boundary on the hemisphere created when it intersects the xy plane, that would be a good start. So this circle is what you would get when you set z equal to 0 in the hemisphere equation, and it's a circle of radius 4, so it's got to be x squared plus y squared equals 16, right? When you set, whoops, too far. When you set this guy equal to 0, that's what you can get. Well, yeah. Okay, and then, so that's the outer part of this base right here. And the inner part is just the unit circle. Just this. Close enough. So that's given by x squared plus y squared equals 1. And we want to set up, we want to integrate over the donut region that looks like this. Because it's above that region that we get the hemisphere, and it keeps us outside of the cylinder in space described by x squared plus y squared equals 1. So does that make sense where the region of integration comes from? Let me go up a little bit. Does that make sense? Okay, so let's set up our integral. It's going to look like something like this. Don't forget r dr d theta. The roof of our structure, we're trying to find volume, the roof of our structure is given by the hemisphere. And remember what that was. That was z equals the square root of 16 minus x squared minus y squared. But when you subtract x squared minus y squared, that's the same as subtracting r squared, isn't it? So you get the square root of 16 minus r squared there. Think about it. R squared is x squared plus y squared. You distribute that negative, you get minus x squared minus y squared. So that's your integrand, right? So let me make sure it's clear where that came from. Z, that's z right there. Just that part. Just the part with the square root. Okay, now, drawing your representative sector. Now, your representative sector doesn't count. This part doesn't count. Just this part to this part, right? My representative sector is just a line segment. Okay, just from here to here. So, okay, so what does r go from then? Inner limits of integration, what r goes from, sometimes they're constant, sometimes you have to write them in terms of theta, but you never write them in terms of r. So r goes from what to what? Well, what's this radius start at right here? That's the 1. And what does it end at? That's 4, right? Square root of this number. So there's your inner limits of integration. And then what does theta run from? Think angularly. Theta equals 0's here. If you keep sweeping out, you keep going around, don't you? Until you get all the way to 2 pi, an angle of 2 pi. So 0 to 2 pi. And you get something that is a heck of a lot easier than what you would get if you tried to do this in rectangular coordinates. Okay, so let's go through this integral. First of all, we can split it up because you have constant limits of integration and just a function of r inside. So make your life easy. Clear up the clutter in your life. I feel like I'm selling you something here. Clear up the clutter. Clear up the clutter in your life and split up the integral is what I'm trying to spit out. So integral 0 to the pi of d theta, that should be. Integral 0 to 2 pi rather, d theta. And then integral from 1 to 4 of square root 16 minus r squared times r dr. Everybody see how I split that up? This first integral is no problem. It's just going to be the upper limit. When the integrand is 1 and the lower limit's 0 and the upper limit's whatever, the answer is going to be the whatever. It's going to be the upper limit. It's just 2 pi. So that's easy. Now this guy, how do we integrate this kind of square root? What are we going to have to do? Use substitution. Okay, what would u be? Okay, what would du be then? If u is 16 minus r squared, du is negative 2r dr, right? Yeah, so we've got an r dr. What do we need? To make it a perfect du, we already have an r. We need a negative 2 in front of it, don't we? But you can't just multiply by negative 2. It's not illegal. So what do you have to do to compensate? Divide or multiply by negative 1/2. Which I'll put right there. Make sense? And then we integrate this as, we can think of this whole thing then as u to the 1/2 du, because that's what this is. This is du. And you don't have to actually make the substitution. This is actually way easier than going through and actually making through the substitution. Once you get used to it, it's easier. It's a little scary at first. Okay, you integrate essentially u to the 1/2 du. What do you get? Leaving it in terms of 16 minus r squared, you get 16 minus r squared to the, okay, you add 1 to the exponent. What is that? 3/2, and then you multiply by the reciprocal or divide by 3/2, which is multiplying by 2/3. And then you evaluate that from 1 to 4. All right, let's clean up what we have out front. What does this become? Negative 2 pi over 3 for now. You're hoping that changes to positive because we're finding volume, right? You don't want your volume to be negative. You know F is positive, so the volume shouldn't be negative. So is that okay on the outside there? Okay, then I do what? Plug in the upper limit first. Now that gets me with just what? 16 minus 4 squared is 0. Okay, 0 to 3/2 is? Just kidding, it's 0. And then what happens when you plug in, subtract off, fundamental theorem, subtract off 1, you get 16 minus 1 squared, which is 15 to the 3/2. So negative 2 pi, well, you can see the negatives are going to cancel, right? Negative 2 pi thirds times negative, you can think of 15 to the 3/2 as 15 root 15, can't you? So what do we get when we multiply the outside of the radical? What do we get? Positive, first of all. Well, 10 pi root 15. What units would that be in if I gave you units?
Units cubed.
Good. Cubic units. Yep. There's your answer.